We are now going to start talking about various cycles that are used throughout industry and the thermodynamics behind them. Today, we start with gas power cycles. This is just the first of a few cycles that we will be dealing with over the next couple weeks. There are two general classifications of cycles, power cycles or refrigeration cycles. The power cycles are subdivided into gas cycles or vapor cycles. Gas cycles involve fluid that remains in the gaseous state throughout the entire cycle, whereas in the vapor cycles, the fluid can exist in both the gas and liquid phases in different parts of the cycle. Another classification that divides the cycles by whether they are open or closed. Closed systems use the same working fluid, whereas open systems have a new mass of fluid during each cycle. We will see versions of all of these throughout the next few classes. Today and the next few videos will focus on various common gas power cycles. This video will focus on gas power cycles in general and get to the simplest version of a gas power cycle called the Carnot cycle. Most devices that produce power operate on cycles. In real devices, there are always going to be some irreversibilities and inefficiencies. A much easier scenario to analyze is the reversible version of the real cycle. This is called the ideal cycle. This actually ends up being not a bad approximation in many cases, and many of the features and results of the analysis for the ideal cycle will still hold for the actual cycle. As usual, cycles are parametrized by their efficiencies, which as usual is what we get out compared to what is put in. For heat engines, we get work out and put heat in. So A to TH, thermal efficiency, equals W net over Q in. And this can also be in per unit mass form or in rate form, as shown down here. It was mentioned that a few approximations are generally used in the analysis. These generally involve the following. There is no friction. This means there is no pressure drop in the fluid as it flows through any pipes. Any expansion or compression occurs as a quasi-equilibrium process. The pipes are well insulated, so there is no heat transfer through them. In other words, the only heat addition or loss are the ones stated, either Q in or Q out. There's no other heat. And finally, any changes in kinetic or potential energies can be neglected. That is, unless there are any nozzles or diffusers involved. Remember that the net work or net heat transfer can be calculated by finding the area enclosed by the cycle on either the TS or PV diagram. Any heat addition will increase the entropy, while any heat rejection will decrease the entropy, and any isentropic process will have a constant entropy. These can be seen on this TS diagram here. 1 to 2 and 2 to 3 involve heat addition, 3 to 4 being an isentropic process, and then 4 to 1 involving heat rejection. The efficiency can then be found by taking the ratio of the area enclosed equal to the net work to the area under the heat addition process, which is equal to the heat in, which would be this area down here. The simplest power cycle is called the Carnot cycle. It is comprised of 4 totally reversible cycles. The first is isothermal heat addition from 1 to 2 on these diagrams over here. The second is an isentropic expansion. The third is an isothermal heat rejection. And the fourth is an isothermal compression. Note that every process here is either isothermal or isentropic. So on a TS diagram, every line is either horizontal or vertical, as seen here. This cycle can be used in either a closed setting, such as a piston cylinder device, or an open setting, such as a compressor turbine arrangement. Also, both gas or vapor cycles can be modeled using this approximation. Because it is fully reversible, it is the most efficient cycle between two heat reservoirs at specified temperatures, TH for the hot reservoir and TL for the cold reservoir. The efficiency in this case is given by A to TH equals 1 minus TL over TH. Note that because these are all totally reversible, this is only a hypothetical cycle that could never be achieved in real life. But like other idealized scenarios, it provides a benchmark to which other cycles can be compared. Any power generation devices use combustion to create the power. In most of these cases, air is mixed with the fuel before combustion, as oxygen is essential. New gases are created in this process, mainly carbon dioxide, which then gets expelled, as new air and fuel mixture comes into the combustion chamber. In practice, this makes the analysis tough as the fluid is constantly changing during each cycle. However, the air-fuel mixture is generally very rich in air compared to the fuel. Air is usually around 90 to 99% of the mixture. Also, air is primarily made of nitrogen, about 80%, and since nitrogen is inert, it does not actually undergo any sort of change. For this reason, some assumptions are generally made for the combustion processes seen during these cycles. These are called the air standard assumptions and consist of the following. The working fluid is air, basically we can ignore the fuel, and it behaves as an ideal gas. All processes in the cycle are internally reversible. The combustion process can be approximated by a heat addition process from some external source. In reality, it comes from an energy release from the chemical reaction of the combustion fuel. And the exhaust process can be approximated by a heat rejection process, which also restores the air to its initial state. This makes it so that we can then treat this air as then restarting the cycle, making this essentially a closed cycle. That is the introduction to cycles and power cycles specifically. Here is your standard pre-lecture example, since we are now at the end of this video, along with the answer. I look forward to answering any questions you may have.